Okay, hi there. So we're going to continue with page 9. Now, this is empirical and molecular formula. Now, girls, please, I've actually given you steps. Just learn the steps. Okay? You don't even have to understand this to do this. You really just have to learn the steps. Go through the steps properly and learn them. I don't know how many times in a test I ask for empirical formula and I get given a whole lot of rubbish because people have not learned the steps. Okay, and it is so easy. Okay, and it's often worth quite a few marks. So if you can do it, just do it. Okay, it's really, really simple. So let me discuss what the difference is between an empirical formula and a molecular formula. So empirical formula is the simplest ratio. Okay, so here it says the simplest whole number ratio, okay, of compounds to each other. So the empirical formula for water is H2O. For every oxygen, there's 2 hydrogens. Butane. Okay, well, let me just talk about the molecular while I'm busy with it. So molecular is the actual formula. So in this case, the empirical formula for water is the same as the molecular formula, okay, because it is in the simplest ratio. Let's just take a look at butane. Now, the end of this year, I'm going to be teaching you how to name organic compounds. So this is one of the organic compounds. And if you look at butane, butane has 4 carbons and 10 hydrogens in its actual molecule, okay? But if you break that down into its simplest ratio, it is a 2:5 ratio, okay? I hope you understand that. So its empirical formula is 2:5. So this is not what it really looks like. It is just its ratio of atoms in its simplest form. So this is what it really looks like, and it is a molecular formula, what it really looks like, and the empirical formula is the simplest ratio. Just getting my periodic table because we're going to need it. Okay, so hydrogen peroxide, for example, is OH because it's H2O2. That is what the molecule looks like, but it's 1:1 ratio, so the empirical formula is HO. Right, so we use percentage composition to calculate the empirical formula. Now, percentage composition is done on weight. Oh my gosh, I'm going to wash my mouth out with soap. It is done with mass, okay? And I'm going to teach you how to do percentage composition next. But what it is, it's saying, so for example, I'm saying here, there's a compound, and this compound contains 30.4% nitrogen in terms of its mass, okay, and 69.6% oxygen. Now, you can't take it as this ratio. The reason why you can't use this ratio to get it into its empirical formula like that is because, remember, you've got different molar masses. So nitrogen could be extremely light and this one could be heavy, and so the ratios are off. Okay, so you can't use the percentage to figure out the empirical formula. You have to get to the moles. When in doubt, mole it out. Okay, so what I want you to do is I want you to always pretend like you're working with 100 grams of the compound. Okay, assume you have 100 grams. Okay, what does that do? Well, we know that 30.4 and 69.6 gives you 100. So if I'm presuming I have 100 grams, which you can always do, that means I can convert those percentages to masses. Okay, so this is actually going to be grams of each of those elements if I considered 100 grams of the compound I was given. Make sense? Okay, so I'm then going to work out the number of moles of each of those. How do I do this? Well, I'm going to use the mass over its molar mass. So that's going to be 30.4 over nitrogen is 14, and I get 30.4 divided by 14, and I get 2.17. You can round off to 2 decimal places. Okay, then the next one is 69.6, and I divided by oxygen's molar mass, which is then 16. Luckily, these are quite similar. So 69.6 divided by 16, and I get 4,35. Now we need to get the simplest ratio of this. The easiest way to do that is to divide both of these by the smallest one. So divide both by 2,17. All right, the smallest one is 2,17. So if you divide 2,17 by 2,17, I get a ratio of 1. And if you divide by the other one, so 4.35 divided by 2.17, and I get this. I don't know if you can see it there. I get 2,0046, blah, 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 blah. But can you see how close it is to 2? I can assume 2. Okay, so the ratio is a 1:2 ratio. So the empirical formula for this compound, based on the percentage composition, is 1 nitrogen to 2 oxygens. And that is my empirical formula. Right, now this is, I can tell you now, this is the same as the molecular formula. So sometimes the empirical formula differs from the molecular formula. Now, this is what you need to do. I say to you, I have these percentages, okay? So now I'm going to give you one that you shouldn't know now, because this is now going to be an organic compound. So I give you two things. Now, how do you know when to use this? Here, I give you percentages, and I tell you the actual compound's molar mass. So this is important. Not only do I give you the percentages, but I also give you the actual molar mass for the real compound, the molecular formula. Okay? Molecular formula. Okay, so of the molecular formula, I can't spell now when I'm talking formula. Okay, that is what it is. So we use the same information. We're going to, because we got percentages, I'm going to just automatically assume or take 100 grams as my given mass for the whole compound. So that means each of these becomes grams. Each of the percentages becomes grams. Now, girls, you can see I've set it up in a table. Some girls actually like to use the table as well. So you're welcome to use the table, but you don't have to. I would discourage you from drawing lines because that just wastes time. But you can put it in this order. So you can go CHO, mass, 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 moles, 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 ratio, ratio, ratio. Okay, I have seen it done like that before and it's perfectly fine. Okay, so again, carbon is, so I'm going to take, here's my number of moles, mass of a molar mass, so 53,55 divided by 12. Okay, 53.55 divided by 12, and I get 4,46. Right, then I'm going to go 9,09 and divide by hydrogen, which is 1, so it's going to be 9,09. Notice how the carbon's mass is, or number of moles is much more, is less than our hydrogen moles. Okay, so you can see even though the mass of carbon was bigger, the number of moles of hydrogen was more. Okay, so that's why we do it like this. Okay, and then 36.36 divided by 16, 36.36 divided by 16, and I get 2,27. Okay, how do I get simplest ratio? You take each one and you divide it by the smallest one. So that's going to be the 1. Okay, 4.46 divided by 2.27, and I get 1.964777. So we can approximate that to 2. Okay, we need a whole number here. Okay, and then this is going to be 9. Okay, because that's going to be, oh, sorry, I lie. Sorry. 9.09 divided by 2.27. And I get 4, and it's 4.0044, but we can assume 4. So my empirical formula will look like this. C2H4O1. Okay, so that's what our empirical is. So now I go, all right, so I need to see if this is the same as the molecular formula. So if I work out the molar mass of what I've just done, okay, and it is the molecular formula, then it should equal 88. So let's work it out. So I've got 2 times 12 plus 4, because we've got 4 hydrogens and they each one, plus 16. Now I know this from before, and I get 44 grams per mole. Problem, hey? Okay, because my empirical formula that I've just got now is 44 grams. But I know that the real molar formula, the real molecule, has a molar mass of 88. So what can you see here? If we times that by 2, we'll get the 88, right? So if I times all of these by 2, therefore my molecular formula is C4H8O2, and that is what it really is, okay, based on the actual molar mass. So I worked out the molar mass for the compound that I got, and if it's the same, then it is the same molecular mass. If it is not, you times, it's always going to be less, so you times by however much you are short. So if it's times, and it's usually times by 2 or times by 3, it's very rare to times by any more than that. Okay, so you'll just compare your molar mass that you made to the molar mass that was given, and you then adjust accordingly. All right, okay, I hope you understand.